to build on this. All right. So, guys, I need us to talk about this. What's happening here? I don't know.
That line is not correct.
Okay, first off, we ain't sweat. I know the line's not pretty. We ain't gonna sweat that right now. We need to focus on the mathematical side of this, though, guys. I'm okay if you don't want to sit in front of the camera because you're scared of the camera. But if you're that far away, it's hard for you to see. Get your tail up here. Don't sit next to each other because y'all like to distract each other. Kaden, all the way over here.
Don't want to be next to you, like close to you, like. You're not shooting, you know each other, right?
I didn't ask. I need you to learn. I need you closer. I need y'all closer. Amber, I need you closer. I need us to be able to, like, the closer you are, the easier it is going to be for you to understand these concepts. Yes?
Okay.
I'm not saying that you got to be 6 inches from me, but I need you at least within the desk. Let's go. This way. Closer. Closer. Mr. Kennedy, I'm struggling. I don't understand. I don't do the things you asked me to do. I'm waiting on students being willing to learn. Thank you. There we go. Finally. Woo. All right. So, listen. I know it's not pretty, the grid. Make sure you're careful about when you're creating scales. The issue here, the reason why the line looks funky is because see how small this is versus how big this is. It's just not an even scale. It happens. Work on it. But that's why the line looks a little funky. So, let's just correct the line a little bit. All right, we want a line through here. That's at least a little bit better. All right. So, this, I'm going to use green to make sure it stands out. This green right here is what I talked about with the group before I left earlier. And we talked about how we got that green. Can anyone from a different group explain to us why my polynomial, the dilated function, is going to be right here in this region? So where are you getting a negative from?
The linear line.
So now do remember, linear means line. So we don't have to say linear line, but what could we call this if it's one of the things we're multiplying? A linear factor. So this linear factor has what type of values?
Negative.
Okay, right? That linear factor has negatives. The parabola, the quadratic factor, has positives. And tell me, Brady, positive times a negative, what does it give me? A negative. That's it. So right here it's negative, right? The nines were asking the question originally, hey, how to tell which way the cubic will be facing? Fun fact, the next half of this unit, we will learn how to figure that out without having to look at the individual factors like this. But when you have the factors like this, that's the best way to do it, okay? So, from here, mark your x-intercepts. I cannot make that more clear because it's where the x-intercepts change, or where we have x-intercepts that the graph can change. Notice right in between here, the two factors have what type of values? What does the quadratic factor have? Positives or negatives?
Negative.
Which one is it? Why do you think positives? So when I look here, it's above the x-axis, so that should be what?
Positive.
Positive? But if you look to the right, positive 2, positive 3, positive 4. Jamie, you look like you don't like that. Why not?
Because I don't know what I'm doing. I don't understand. I don't know. I just don't know.
Okay. Stay calm, don't figure yourself out. Just ask a question.
Mr. Kenny, I don't know what to ask. I am calm. I just asked. Be calm?
Yeah, where you
calm.
Be calm.
Bro, look, let's focus on
you doing a little thing. Hey, you gotta mark your x-intercept.
I mark the x-intercept. Okay, but Jamie, I want you to look. So I'm looking. Remember, guys, I already looked to the left of this x-intercept. Now I'm looking in between these two x-intercepts. If I look at this quadratic factor right here, in between the x-intercepts, are those outputs positive or negative?
Positive.
Why do you think they're positive, Akari?
Because it's past the x-intercept. It's up this line.
So we see the x-axis?
Yes, sir.
Hey guys, what's the y value on the x-axis? Y is equal to?
X plus 2.
If we're on the x-axis, what is y? 0. So if you're above the x-axis, the y values are positive. If it's below the x-axis, the y values are negative. So it's all about the output. So Jamie, see how this right here is above the x-axis? So those values are what? Positive. What about this linear factor? Positive or negative? Is it above or below the x-axis?
Below.
So if we're above 0, is it positive or negative? Okay. That's it. And what do I get when I do a positive times a positive? So I'm going from this 0 into the positives, but it's got to turn around and go back to the next what?
0.
It's got to get to the next 0. Right there. So it went into the positives, got to go back to 0. Now I got to figure out what's going to happen after that 0. Now, once again, I'm going to look at how many factors do I have? 2. I have a,
Positive and negative.
well, which one's positive, which factor?
That one.
What is this one going to be called? A linear factor is positive. The quadratic factor is negative. Why is this negative down here?
Because it's below the x-axis.
Remember, the x-axis has a y value of 0, and Brady, what's below 0? Negatives. That's it. Positives and negatives. And what do I get when I take a positive and I multiply by a negative? So, this polynomial, this new one, goes down, and then it's got to turn around and get back to the what?
Positive.
The 0.
To the 0. Remember, it's more about the zeros than anything else, because it doesn't always have to go into the positives. We're going to talk about that soon. And then to the right here, my linear factor has what type of values?
Positive.
And quadratic?
Negative. And then positive.
Are they above the x-axis?
Oh, yeah, positive.
And what's a positive times a positive?
Positive, negative.
So that is my polynomial. Specifically, what type of polynomial is this? How do you know it's a cubic?
It has 3 zeros.
There we go. It's like we're learning something. Look,
What's that E word?
1, 2, 3 zeros. It has 3 zeros, so it has to be third degree. That's what you're going for, Taj? That's what I was hoping I was hearing? You said D word, right? Degree? Yeah. So remember, 3 zeros, third degree, cubic function. And so we want to keep all those things in mind. So what questions do you have about sketching this function, about positives and negatives before we move forward?
No question.
Preston seems good. Taj is good. No, I'm not going to give you any more practice at all.
Any sarcastic thing? Or demonstrations?
Jamie, questions? Still looking a little irritated.
I'm not gonna lie, you had this little cubic thing, just the active thing. I mean, just looking now, it's kind of like, huh?
All right.
Yeah, X plus 2.
It's looking like y'all are done with your questions. We got this here. Hey, really quickly. Hey, if I can grab your attention really quickly, I want to just point this out about the way this is graphed right here. I get this. Please notice on this side how it almost looks like this polynomial is a line, right?
Yeah.
But remember, what's happening with our outputs? They're being multiplied, right? So one thing to think about is this. If I'm taking this number 8 here, and I'm multiplying it by, I don't know, -1, what's 8 times -1?
Negative.
-8. See how it's significantly steeper? In general, when we create these higher degree polynomials, specifically this is that cubic, right? It's going to be really steep on the edges. It's not going to be, like it's never going to get vertical. It's not perfectly vertical. But do notice how it's going to be pretty steep, okay? And that's because what we're doing is we're taking really big y values and multiplying it by really big y values. And so it's just going to get bigger and bigger and bigger and bigger. Right, so keep that in mind that it's going to get steep, not go out. Like positives and negatives are fine, but those are a conceptual piece that I do want us to note and pay attention to. All right. Does that fully answer y'all's question, by the way, about the shape and how it starts?
Yes, sir.
Okay. What's up, Bakari?
Yeah, I kind of understand how you did the cubic function, why it went.
So it's all about those zeros, those positives, and those negatives. Remember, mark your zeros first, because wherever there's a 0, that's where it can change from positive, negative, etc. Oh, I meant to pull this up so it was easier to see. Oh well. All right. today we got to finish Desmos, and then we're going to get into lesson 4, and then concepts. We're going to be talking more about fundamental theorem of algebra, something called multiplicity. It ties into double and triple roots and things like that we've kind of mentioned. And then how can we use factors of polynomial to determine the graph? And tomorrow you are going to finally have a demonstrated understanding on sketching polynomials from factors. So we are going to get some more practice today with these ideas. Before I actually move forward though, Taj broke my heart and still hasn't done a Hero Friday. So can I get someone else to do a Hero Friday tomorrow?
So we do the mathematician Monday, Mr.
Yes, Kenny.
Kenny won't do it.
Yeah, we
Huh?
We do mathematician Monday.
You gonna do it, Taj?
No, it's what I'm talking about.
Yeah, he said he gonna do his brother.
Oh.
Like talk about his brother.
See, that's what I'm gonna do this.
Why?
My
We can do Taj and Winner.
Alright.
Wait, when are you gonna do mathematician Monday, Mr. Kenny?
Go ahead.
When he do it? When he do it?
Because he didn't do it at all. He said when do it
Let's-
all week.
Let's
Is it
do
that
this.
important?
My
He said he gonna do
plan.
it later on this week.
Yeah.
This is later on.
This is later on this week. My plan was to do it right after we finish the Desmos activity. We hadn't finished the Desmos activity yet, and then tomorrow's Hero Friday. So I'll just have to do it this upcoming Monday.
Okay.
Never mind, this upcoming Monday we won't be in school, so I'll have to do it. I'll just do it on Tuesday. Veterans Day. Okay. So,
I'm not coming tomorrow.
hey guys. So we're gonna have Veterans Day on Monday. I'll just do that Hero or the Mathematician Monday on Tuesday.
Is we coming to
And introduce you to Francois Vieta. All right. So one thing I really want to quickly point out: this foundation piece, that zero product property. That was on our last test. It was in our last unit, and some of us did fine on it on the test. But I need to make sure that this is clear. Earlier, we had this function, right? X minus 2 times x plus 1. And then we dilated it by x plus 2, right? Let's call this function h of x. Now, if I want the zeros of this function, what's the first thing I got to do?
I mean, no.
Well, I'm not adding it, but I can set it equal to... Well, first, I gotta set it equal to 0. So I can't separate it yet. Because the whole idea is that I have a what now? If I have factored form, what do I have at the end of those factors? I'm multiplying, it starts with a p.
Polynomial.
I have a product. If I'm talking about factors, right, I got a product, and I got a product of what? I got a product of 0. Literally, there's a product of 0 here. So, what property can I use if I have a product of 0? Zero product property. Guys, the whole point of why the zero product property works is this. If I take 2 times 3 times 5, will that give me a product of 0? No. If I have 2 and 3, what do I have to multiply it by to get a product of 0? 0. The only way to get a product of 0 is if you're multiplying by a 0. That's why the fundamental or the zero product property works. The only way to get a product of 0 is if you multiply by 0. So either x minus 2 equals 0, x plus 1 is equal to 0, or x plus 2 is equal to 0. One of my factors has to equal 0. This whole unit on polynomials is all about the factors, okay? So that zero product property, one of those factors has to equal 0. That's how we get our zeros from there. You go with me on that, Brady? Okay? Now, determining if a polynomial in standard form and in factored form are equivalent. We're going to get more into that later, so I'm not going to stress it right now, but that is foundation that we should know. We should know zeros, factors, the whole 9 from there. This target is what we have been working on of sketching polynomials when given the graphs of their factors. Or sketching polynomials when given the factored form of the polynomial or when asked to dilate a polynomial by a new factor. That's what we actively just did, but in order to do this, you have to do this piece. And then what did we focus on in order to sketch those polynomials? If the values are positive, 0, or negative. It's all about the positives and negatives. There's other ways to get these functions, but understanding our polynomials through those is critical. what we're about to get into, hopefully these terms sound familiar. Domain and range. What do we mean by domain?
I can't even remember it.
I didn't know.
Yeah, I heard the word. I remember it.
We heard the word, but we don't remember it.
Yeah, I've heard.
Like, is the domain like the,
I forgot how to do it.
like the sectors on, what's it called?
The what?
Like, you see how
Say it again, Jamie.
It's the X or something.
It's something with the X. Does that jog memories?
it's there, no,
Maybe?
An example,
Might as well
please.
just
An
give
example.
Okay, so we'll have to look at examples soon. Okay? Please. I'll go ahead and give this background. It's the set of all X values for the function. The range then is the set of all Y values for the function. We're going to practice on how to identify that, but yeah, we got to know domain and range. That also, if you remember, was on a Mathia assignment, the e-learning day assignment that I still haven't put in, but I will be putting in ASAP. So yeah, e-learning day assignment and intercepts of polynomial functions. Hey, Kenzie. Determining the standard form of a polynomial by multiplying linear and quadratic factors. You already know how to do this. We're going to get practice with that in a second.
Excuse me.
We're going to talk more about degree in a second, multiplicity as well. So pretty much all of this proficiency scale is what we're doing today. But y'all need to finish the Desmos activity. I got to speed things up, so I'm not actually going to have y'all log on to Desmos. Here's what we're going to do. Brady, I can get past it. Oh, I got to get my chair.
Kind of needs his chair.
Okay.
Stop throwing things around you, Michael Watson. I'm not playing with you.
Yeah, she's not playing with you.
I ain't got nothing in my hand.
Because it's over here.
But J Mike also. Come on, dude. You know better.
Oh, you ain't either.
Okay.
It's another one.
All right.
No, no,
You ain't it.
All right. If I can get your attention,
Come on now.
right here on the board, through the Desmos activity, we have what type of function?
Quadratic. No. Yeah, no, quadratic.
Cubic.
Which type of polynomial? A cubic. How do we know that this is going to be a cubic?
It has 3 zeros.
All right, it's 3 zeros. I would also point out what's creating those 3 zeros.
Linear.
3 linear functions.
Yeah, three
Right?
linear functions.
We've talked about this, right? 3 linear functions is going to create a cubic. Because each linear function has how many zeros?
3.
Well, each one has 1, and so we're going to have 3 different roots here. Now, this is an example of what this looks like when we have 3 different roots, okay? So this is 3 different roots. What I want you to compare that to in a second is I'm going to construct, actually I'm going to have y'all do it, construct a few cubic functions such that 2 of the factors have the same root. Alright, so what I need someone to do is I need someone to go over to my computer and I need you to change one of the linear functions so that we get the same root for 2 of those factors. Alright, Ricari, let's try it. Let's see what happens when he changes it so that we have
the A slide.
so change any of those sliders so that we get the same root at one of those locations. Alright? Do we now have the same root?
No.
No?
What's that smell?
You?
Mr. King.
Can anyone find it?
Did you have one?
Back.
I think he did just have one. There you go, Cameron. Help him out.
Yeah, help him out, Cam.
He's getting close.
There we go. Right there.
All right. Do 2 of the factors now share a root?
Yes.
Okay. So because 2 of the factors share a root, and what are we going to call this root?
Why no?
Double root.
This is going to be called a double root.
I remember that.
Okay. This is also going to be, we can also say this is x equals -2 with a multiplicity of 2. This over here would be x equals 1 with a multiplicity of, any guesses? Say it again. Say it louder.
Uno.
1. So why does this have a multiplicity of 2?
Because it's 2. Because it's negative 2.
I
can't see it.
Well, you could stand up, you could move around the room to be able to see the board more easily. In fact, if you're in the 2s, it's probably going to be really hard to see this. You might need to move around, otherwise you're just literally saying, I don't care about learning.
Or that one don't pay attention.
Multiplicity of 2. Why is it a multiplicity of 2? Okay. Let's do this. I hear why y'all are thinking, someone's thinking negative 2. Can you move out of the way really quickly, Corey? Alright? Alright, so I've reset things a little bit. Thank you.
Good job, Ray.
Alright, so I've reset things a little bit. I need someone else to come up here and create a cubic such that one of the roots is shared. So somebody else.
He's trying to volunteer, so he gotta go.
Now, I was asking, did they want to?
Hey, Ricard, let people volunteer themselves. Okay.
Oh, what you trying to do?
Can I get somebody to come create a cubic such that two of the factors have the same root?
Let's go, Gianna.
Thank you, J. Mike.
We don't give them behind me.
Want to be there?
Okay, you can do it that way. Does that work? Do we have the same root?
Yeah.
Okay, so right here, I'm going to call this a double root. I would also say, or I could also say, x equals 0 with a multiplicity of what?
2.
Why is it 2?
It's got 2 roots.
It's got 2 lines going through it, right?
Did I see that? Just
I saw it flying. So what I would also point out is this. It was not J. Mike, it was from over there. I don't know. Look, this would be x equals...
You threw it.
X equals what?
0. Because the dot's on 0, right?
Now you see.
That's
Oh,
a
I'm
0
thinking that
and 4
one.
with a multiplicity of
1.
1. Here's what I would point out. Quite literally, let's say I look at this linear function, the red one. What is its 0? It's 0, right? This linear function, what is its 0?
0.
How many times do I get x equals 0? Twice, so the multiplicity is 2. The multiplicity, okay, and we're going to look at this in the book in a second, but I just need you to understand the multiplicity of a 0 is how many times. It sounds so much like a phone.
Oh, no, that's
Sorry,
Sounds like an OtterBox case. Alright, multiplicity of 0 is how many times that value, whatever case. So guys, how many times is this a 0?
1.
This 4. It's only one time, so the multiplicity is
1.
1.
We shouldn't go.
Now, we are about to go, but before that, guys, right here, please.
Hey, we're not leaving yet.
Yo, we're not leaving yet. Rock hand, bro. Hey,
We still paying attention, Mr.
Screen for y'all, screen for you.
Guys, hey, Tosh. What we're going to have to talk about when we come back, or hopefully get it right now, how is, Tyler, how is the behavior at this 0 different from the behavior at this 0?
Because on one singular point.
Right, but what's happening here with the polynomial, the cubic here versus here?
Just because on y instead of y is 0 twice, Ms. Kendrick.
What's happening? How is it behaving differently?
Well, they got a drastic drop in it. Something like that.
Is that the 0?
We're talking about when we get back to the
Get it, OG.
You got Mark over there. Hey, Tyler. One. Again, Hood. Jaquel, Hood. J. Mike. And Cameron. That's all. Thank you. And Brady. I didn't even know she had a hat on.
I didn't.
Hey, Tyler. Phone up, please. Thank you, sir.
Dude, it's recorded. Get out of the way.
Whose phone it is? It shouldn't be out. And I need the basketball.
Make it fair.
What's the hash tone, Tyler?
I need the basketball. Thank you. Alright, I'm going to use this in a second, but I need us talking, I need us thinking. I'm going to use it to help y'all understand something. Tyler, Alexis, attention needs to be up here so that you can grow and learn. Alright, so once again, what I need us to understand, and Preston, I need you to quit doing that. Wear down my markers. No.
Yes,
I need you to quit. That's not what I'm saying. I need you to quit drawing on the desk. It's wearing out the markers quicker than I can replace them. Yep. It's to the point where I had to start spending my own money on the expo markers and not even the school giving money. So, right here, what I want us to talk about is how is the function behaving differently at these x-intercepts that are double roots versus when it's not a double root. How does the x-intercept behave differently when we have a double root versus a non-double root?
Well, cause I mean we have a. What you said again? It's like you went a little bit fast. So much words. Say that one more time, please. Just a lot of words.
So, right here,
Right.
each of these x-intercepts would be what kind of root? Or what multiplicity?
3.
Each one,
Cubic. I mean,
each root, and lights one please. Each 0 happens how many times?
1 each.
Once, right? So, notice how through here, when I look at this 0, there's that. Right here it's behaving this way, right here it's behaving this way. How is that behavior around that x-intercept different from when it is like this? What's happening differently with this x-intercept right here?
It's correct.
Well, it goes down afterwards, yes. Okay, so what you're kind of pointing out, I guess, let me see if I understand this correctly. Thank you very much. Let me see if I understand this correctly. What we're looking at here is you're saying, hey, it's hit this intercept and it keeps going up?
I know it's new.
Who said that? Oh, Preston. So you're saying it's going up through there? But here it's going down, right? But remember, it is increasing to here, right? So there's a couple of things that we want to talk about with this. Let's see if I can change the... What?
Is that not what it's called? At the very top?
Damn, this is you.
It is called a maximum. You talk about the climax in your English classes. The climax is the pinnacle of the action in the story before the falling action and the denouement.
Yeah, you should be
So, how about this? I want you to think about this as if this was a basketball. If I take this basketball, right, and let's pretend like, can you hit the, okay, let's pretend like this x-axis is the floor, right? When I throw this basketball, or I, not necessarily throw it, but when I bounce it, I'm going to bounce it, you can't see, I'm going to get your hands out, okay? When I take this basketball and I bounce it, right, or I throw it to him, give it away. When it touches the floor, what's it doing?
It goes up. It goes hits the ground.
So it goes down, it bounces, and then what?
Goes up.
Comes back up. Right here. How are we going to describe this? It's going
Like
down.
a basketball, basically. Hitting the floor, then going up.
Okay, but what's the terminology I just used? It's going down, and then it what?
Goes up.
It bounces.
Oh, okay.
What's happening at this x-intercept? It is
Goes down and it bounces.
bounces. So, when there is a double root, what's happening at that x-intercept? It bounces. Let's look at it from this other side. Okay? So let's change it back to here. I know it's underneath, but let's say I were to take this basketball and I throw it up at the ceiling. If it was a nice solid ceiling, what would it do? It would hit the ceiling and then what?
Go down.
It would
Bounce down.
bounce back down, right? Okay? No. So what are we trying to say? What am I trying to point out here? When it's a double root, right?
Yeah.
It bounces at the what? So if you have a double root, remember that means it's a multiplicity of what? Multiplicity of 2. The function bounces at the x-intercept. Wow, did it drop again? So look, hey guys.
Who was in my paper?
No, that's she's how you did.
Hey guys.
No, I'm trying to get you all to pay attention instead of talk about things that don't relate to the math. So right here, I just need us to recognize when it's a double root, it's going to bounce. That's it. And here's what I would point out, and I want you to see. If you were using the positives and the negatives, this is how that would work. So I will note, and we want to pay attention here, how many factors does this function actually have? How many factors does this green polynomial have?
2.
I see 2, but remember, it's got to be 3.
It's 3, I see right now.
If you look here at the red and the, excuse me, if you look at the red and the black, they are the same exact line, right? So we still have how many linear factors here? 3. We still have 3. There's just 2 of them that are exactly the same. So I need us to pay attention to that, because that's a possibility where you have 2 factors or even 3 factors that are exactly the same, but we still have how many factors here?
2. 3. 4.
Got 3, guys. We've got 3 factors. So I need to pay attention to 3 positives and negatives. So when I look right here, are these positive or negative? And how many positives do I have?
2.
I have, sorry, remember there's 2 factors and both factors have what type of values?
2.
Positive. And then these are negatives. So what do I get?
Negative.
Negative. Brady, why do I get a negative here? Remember, there's something I explicitly talked about with you.
Right now.
Because the positive becomes positive.
Yes, but there's something I talked about with you. Do you remember what we talked about?
I forgot it.
So remember, if it's an even number of negatives, it becomes what?
Negative. I mean, even number of negatives.
If I have an even number of negatives,
Yes.
what does it become?
Positive.
Okay?
If you have an uneven amount of negatives, it becomes a negative.
What's another term for not even? Odd number. Odd number, right? So, Brady, right here, even or odd number of negatives?
Odd.
Odd. So it is going to be
Negative.
negative. So notice all of these values are what?
Negative.
Negative. Now I look in between these x-intercepts. All of these values are what? Negative. But how many do I have right here again? How many factors?
1.
Sorry, just right here.
2.
2. And then this factor has what kind of values? And notice, do I have an even or odd number of negatives at this point? I have an odd number, so what is the final values? Negative. And so notice, it goes from being negative back to being what? Remember, this is negative. Notice, does this go through the x-axis? No. It is negative values, it touches, and then it bounces away back into the negatives. That's the only way you go from something back to itself, is if it touches and bounces. If you have a double root, that's how that happens. Okay?
Okay.
But then, we keep going along, keep going along, keep going along, then we get over to here, and these values, this factor has what type of values? And then these have,
Negative.
but how many negatives?
Yeah.
2, right? So a negative times a negative times a positive is positive.
Oh, okay.
So, go back there.
I got the pass out of this.
Oh my gosh.
Yes, it's very hot in here, Mr. King.
I mean, I'm always down to turn it down, but.
I like when cold Mr. King outside.
Alright. Alright. So, here's what I need y'all to notice, and I need you to pay attention to. If it's a single root, what's the function going to do with that x-intercept? It's going to go through it, okay? If it's a double root, it's going to bounce off of it. So if it was already positive, it would bounce and then go back to being positive. If it's already negative, it's going to bounce and go back to being negative. But what about, and this is the final detail before I have you do some notes to your future forgetful self, what about if there was a multiplicity of 3? What
So
would
triple?
that'd be a triple root?
Triple
But what do you
root,
think it's going to look like if there's a multiplicity of 3 there?
It'd be 3 roots and then it'd be like a cubic function.
Now, well, be careful. Yes, there's 3 roots, and it would be cubic because it's got 3 roots. But
Right.
my question is, how's it going to behave at that x-intercept?
So basically, if 2 roots like together like that way, and there was 1 root by itself, that's what you're asking us?
No, I want all 3 roots to be the same. So, I need someone to come up here. It doesn't look like we have an idea, and that's perfect because I'd be surprised if we did. I need someone to manipulate those 3 linear factors so that we have the same root for all 3 of them. Okay, Mike said, I got this.
Let me see. You can't trouble it.
Just like it.
Okay. Alright, so now we got a double root. How do we know it's a double? Oh, go back. How do we know that's a double? Hey, you're going to have to change two different lines, buddy. So that's a double. How do we know it's a double? Because they're both right there in the, also, what's happening to our polynomial? It is bouncing. But I will point out, like red and blue are together, or red and black are together. Now you got to get this blue one over there. How are you going to do it? I will make this suggestion. I would probably move my y-intercept instead of my slope. And you can ignore me, but I would do the y-intercept.
Oh, I'm sure. My bad. See though. Yeah, you're right. Oh, no.
The D is your y-intercept. You're going to have to change your slope probably. Oh, there we go. So,
That's all I'm trying to say. Like, how would it be if
Okay.
all was like that?
so what's happening when it's a multiplicity of 3? What's happening to the function?
Being,
Is it bouncing again?
running
Now,
straight
be
through?
careful. Is it going straight through like this?
No.
No.
There's something that goes that way.
So, it's curving through. Guys, when we have a triple root like this, Kamaya, you with me? Because I see you working with James here, but I need us, because Brady's like directly in front of you, so.
Yeah, he is.
So, here's what we need to notice. When it was 3 different roots, remember, it did just go straight through. When it was 2 different roots, meaning we had 1 root that was a double root, what was happening? It bounces, right? So, double root. So, double roots bounce. But what about if it's a triple root? What's happening here? Is it going to go through like it does when it's a multiplicity of 1?
No.
It's going to curve through, right? So when you see a curve like this through, which that's probably a higher multiplicity, when it curves through like this, how many x-intercepts do we have?
2, 3, 4.
3.
How many x-intercepts do you have? You have 1.
Oh.
But that 1, 0 has what multiplicity?
3.
Okay, so even though it only has 1 x-intercept, it still has a multiplicity of 3, so how many roots does it still have? 3. And what type of function is it still?
Cubic.
Cubic, right? A cubic, or 3rd degree. So remember, the number of zeros needs to include the multiplicity. It is not just how many different zeros it has. It is not just how many x-intercepts it has. It is quite literally, we have to count up all the roots, right? So this one only had how many x-intercepts? 2.
Is that
But how many roots did it have?
3.
It had 3 roots, right? 1, 2, 3. Notice how I said 1, 2 roots and the 3rd root?
So it's called double bounce.
So, well, no, that's just pointing out graphically double roots bounce.
Okay.
Well, I should say polynomials bounce at double roots. Okay? And then over here, what's happening with the triple root? The polynomial curves through
Curves.
the x-axis at triple roots. Which, remember, a triple root would have what multiplicity? What multiplicity would the triple root have? A third, or multiplicity of 3, yeah. Okay, so you have your Frere models. What I would do is I would get them out the first page, and some of us need to wake up a little bit.
I've been answering all the questions.
I know, but you gotta get it down, you gotta be worried. So,
Hey, I would take it.
guys, quite literally, at the bottom right-hand side or corner, it says multiplicity and behavior around such roots.
What pages?
The very first page, Vakari,
Okay.
bottom right, multiplicity and behavior around such roots.
Y'all know my school playing yesterday.
Okay.
I'm gonna take the kids off like that.
One thing I do want to point out, I know some of y'all are still taking notes, please continue, this will help Vakari in a second. I want to just point this out. So this in purple right here is this exact cubic function, this green one right here, okay? The way I did that was I went to the computer and I said, okay, the computer has f of x times g of x times j of x, and I just identified the equations from the computer. So, I want to ask you, how could I use this equation to find the zeros for that green cubic function? How could I use that equation? And so that's going to be something I would probably write down in that multiplicity area. How could I use that equation to find my zeros? Set the whole function equal to what?
0.
Right. Remember, if I want zeros, what is my output? I'm not trying to trick you. If I want zeros, what's my output? 0. That's why it's called zeros. Because I'll point this out, like if I was looking at that equation, I would never have thought that my zeros or my roots were all the same. But what can I now do now that this function is set equal to 0? I can use something really, really important.
Zero product property.
Thank you. Good job. Sorry, I'm trying to use different colors. Thanks. Yes. I know, your life is rough. All right, negative 0.5x plus 1 is equal to 0. Negative 2x plus 4 is equal to 0. And 2x minus 4 is equal to 0. The only way that we have a product of 0 is if one of those factors equals what? 0. That's the zero product property. The only way we have a product of 0 is if one factor is equal to 0. So now what can I do to solve these equations?
Hold on. I was wrong. You said one time, please.
The zero product property. You've heard that before, right? What's it?
Use it only in factor form.
Yeah, but what does it mean? Yes, we only use it in
finding
factor form.
zeros.
Huh?
Finding zeros.
That's what we use it for, but my question is, why does it work?
Because it shows what x equals.
I mean, that's a benefit of it.
Right.
Hey, Vicard, let me ask you this. What is the only way to multiply numbers together and get a product of 0?
By multiplying a number by 0?
Oh, okay. So one of the factors has to equal 0?
Yes.
That's the zero product property. If this product is 0, one of the factors has to equal 0.
Right.
So I set each factor equal to 0. Okay. What do I now do to solve this equation? Subtract 1. Negative 0.5x is equal to negative 1. What do I now do? Divide by negative 0.5. Anybody got a calculator handy? Can someone pick up a calculator? Because I see at least 3 right here. Tyler took care of this group. Nope. Nope. I literally praised you for grabbing calculators for your group, Tyler. Like, why are you getting weird about that? Oh my gosh. Negative 1 divided by negative 0.5. Negative 1 divided by negative 0.5. The thing on the board. It's not 0.5.
It's 2.
Okay, is it not 2?
It's 2.
It is 2.
Yeah, what did I say?
I did that.
Negative 0.5 is what you said.
I need a book.
Okay. Minus 4. Minus 4. Negative 4 divided by negative 2 is 2. Jamie.
What?
Is it not Jamie?
No, it's Macaria.
Macaria.
No, it's Ain't even singing today.
My bad, Jamie. I messed up.
Inappropriate song. I was thinking.
Look,
I ain't even there.
I need y'all to look at this. When I solved I said each of those factors equals 0 and I solved them, what did x equal every single time? X was equal to 2. Remember, we set the factor equal to 0, Addison, but what is each 0? Each 0 is 2. So we would say that my zeros are x equals 2 with a multiplicity of what? That's what it is. By the way, what did we see graphically earlier for the zeros? X was equal to 1, 2. So, I need us to notice that they're telling all the same story. The way we find our zeros, what we're seeing graphically, what we're seeing algebraically, they're all telling the same story. Okay? No matter what, our zeros our multiplicity is how many times that number is a 0. You can use your zero product property with the factored form. You can see it graphically, whatever you need to do. But they're there. And if it's a multiplicity of 3, if it's a triple root, what's going to happen at that root?
It's going to go straight this. It's going to curve through.
It's going to curve through it. Whereas if it's a multiplicity of 2, it's going to bounce. And if it's a multiplicity of 1, it's just going to go pretty much straight through it. It's not a line, but it does go straight through it. It could go up too. Don't forget, like it can go up, but it's not going to curve through it. It's not going to bounce. It's going to look like that.
It's some type of puppet, but I forgot the name of it.
Okay. We should have all the notes we needed down. I will wait if you want to continue to get that information using that equation down to sketch the graph, but we're going to start back in 2 minutes. You have until 1:30 before we start moving
Okay, now
in.
look here. We talking about were you talking about the multiplicative? Like you saying something that'll tell you if people are on the board. Can you write on the board?
Because the multiplicity is how many times that value is a 0.
Okay.
Come on, babe. Just calm down.
Damn, what's that thing? Baby,
You stupid clown.
it's usually big.
Hey, you, Mr. Penny.
It's a
Yes. Yeah.
I am locked in. I have been my nose.
So Mr. Kenny don't look like that. He just look like
No, I'm not what you be calling me.
Mr. Kenny.
You know, you want to talk about
He
graduation?
wasn't here. He asked me to do it now.
You know what
Have to go
Jamie
to
be calling you?
graduation. Huh?
He answered to it.
Oh, I don't know. It was like an absolute. You just answered to it.
Mr. Kenny Benny.
Mr. Kenny what?
Benny.
Kenny, Benny, Lenny. I love that name.
Do all the teachers have to go to graduation?
Yes.
Oh,
Man, I'd be mad.
That's something to teach.
Having to sit there for like 3 hours.
All right.
Watch some kids that you don't know.
So, really quickly, okay, do we have, get introduction from over here, just this part, okay. So, guys, I need you to remember this, and we talked about this yesterday, but, hey, right here. Hey. Thought you were locked in.
I'm locked in.
Uh-huh.
On the game.
Fundamental theorem of algebra, okay? This is the really technical way to say it, but the fundamental theorem of algebra states that any polynomial equation of degree n must have exactly n complex roots or solutions. Now, when we say complex, that means that those numbers could be one of two things. Complex numbers means they could be
Say it again.
Complex numbers.
They're all numbers.
They could be imaginary.
They can be positive.
They could be what?
Imaginary.
Imaginary or well, yes, but whole is a bigger of real, right? Your complex numbers, right, are the real numbers and the imaginary numbers. So when we say if I tell you, hey, we have a function.
Shut up, I'm calling
Oh, frick. If I tell you that, if I have that function, how many zeros does that function have? How many roots?
3.
3. Yeah. Will I see all 3 of them on the x-axis?
No.
Yeah, no.
No.
Yes, on the stone. Yes, unless they're all.
Because some of them could be what?
Invisible.
We're going to study this more later, but right here, how many x-intercepts does this have?
Who knows?
It only has 1, right? 1 x-intercept. What would be the multiplicity of that root right there? I'm going to make it up. Say x equals -3, multiplicity of... It's only 1. But that's a cubic function. It should have how many zeros?
3.
Should have
Oh,
3,
wait, oh.
right? Cubic, 3rd degree, 3 roots, 3 zeros, right?
Yeah.
So where are the other 2?
Yeah, the group we have.
They're imaginary. I can't see them. Notice, this is similar to the shape of every cubic we've seen, right?
Yep.
That has the same shape as a cubic function. You need to hold on to the shapes of cubic functions. We're going to explore them and understand them more later. But it's important to recognize that it's just about complex roots, so you can't always see them. Sometimes you can. For example, right here, I only see 2 x-intercepts, but how many roots are there? That's 3 roots, right? 1, 2, 3. But sometimes you can't even see some of those roots. So you have to understand the shape of a cubic function to know how many real roots it has and how many imaginary roots it has. You can also see it from the equations. But fundamental theorem of algebra, whatever the degree is, that's how many roots it will have to have. I'm going to use that in... Sorry, I'm trying to think about time. Let's do this. I think this would be a good place to be. You tore this page out of the book the other day. We'll end on this page. Page 168. It says determine the degree. We'll go ahead and get page 168 out.
You said page 160 what?
8. You tore it out of the textbook the other day.
166. He got
If only Preston was as funny as he thinks he is.
Real. Thought as much as he knew.
I don't think I know that much.
Good.
I always got more to learn.
I know a lot.
I never said you didn't. I just said you're not as funny as you think you are.
Don't play with it, buddy.
What's the page? What's the day?
Okay. Yes, Kennedy.
I'm sorry.
I told you wrong.
What's up?
I told you.
You didn't get that page torn out the other day?
Bye. I'm so done. Like, he cooked his own hair. Okay, son. Today. I'm sorry, you can have a transition. Blood to crip Blood to crip transition.
Kennedy, here's most of the pages from that, but it's missing the few. I'll define the rest. It's missing just that first page. Yes, Alexis? Okay, let's go ahead and get people started, okay? I will try to find it for those who don't have it in a second. But page 168 has this there. Now, I'm going to get us started and point this out, okay? What I want you to do is 1, find the degree of each function, and 2, find the zeros and their multiplicity. So when I look at A up here, what degree is f of x?
Polynomials?
What degree is it?
3, 1, D1. Never mind.
Degree 1?
First degree.
D1.
It's x to the first. What would my 0 be? How would I find my 0 for zeros?
X
Oh, wait,
minus.
no, you just put 0.
You just set it equal to 0. So I actually only have 1 0 in this case. It's x equals 0. With g of x, what degree is g of x?
1.
So first degree. And then how would I find what my 0 or zeros are?
0 equals x minus 1.
So 0 is equal to x minus 1.
And you do plus 1 to each side, and then x equals 1.
So x equals 1 with what multiplicity?
1.
Okay. I want you now to find the degrees of each of those functions and the zeros and their multiplicity. So talk for just a couple minutes on these. We'll come back and talk about a couple of them in just a minute. So work with each other to find the degrees.
But it's all
On the, yeah. Stay on screen for that.
What about your learning?
never say that. Never say that again.
Stay on, you gotta be, oh, nuggets.
You're not supposed to have it. You're supposed to put that on there.
I was about to put it in.
Mr. Kenny, Brady has his phone. Brady has his phone.
Brady has his phone. Pressing. Worry about your learning.
Uh-oh, academically successful.
Get out of the
Great clip.
great tips.
What's the haircut place called? Great clip. It was though.
Okay. Kennedy, I'm still trying to find it. I'll find it before tomorrow. Actually, I'll just print one out for you. Have it class. All right, so C. What degree is C?
Second degree.
Okay, so Vicari thinks second degree. Why second degree?
Because it's 2x. Yeah, second degree. 2x.
Be careful about that, right? What if I had... What degree do you think this would be if you're going to say it's because there's two x's?
That's 3x.
Third degree.
So this would be third degree. So it's not just counting up the number of x's. Be careful about that. Because notice, what type of function is this?
Exponential. Oh, wait. Oh, no.
Just this piece is
Vacuum.
quadratic. How many zeros is this quadratic going to have? 2 zeros. This is linear and going to have how many zeros?
1.
So how many total zeros are there?
Trace.
So what degree would it be?
3.
Third. So please notice, what I'm trying to point out here is, don't just look at how many x's there are. Think about how many zeros there are. Each factor has their own number of zeros. So like when I look at h of x right here, how many zeros does this have? 1 0. How many zeros does this have?
1.
And so what degree is this going to be? How many zeros right here?
2.
No, just the x minus 1.
1.
How many zeros right here?
1.
So,
2.
2 zeros, so second degree. So what are these last three, or last two going to be?
3.
Third degree.
We did not get a chance to look at the multiplicities. I need you to find your zeros and your multiplicities tonight, and we're going to talk about it before you're demonstrating understanding. If you don't take the time to find your or find your zeros and their multiplicity, the demonstrating understanding will be harder for you. Take the time to find those zeros and their multiplicities.
Can I stop it? Mr. Kenny.
Yes, please stop it.